All right, today we are actually going to be kind of connecting what we did yesterday, making a sample space using a tree diagram, a list, or using a table, and then also learning about a mathematical principle called the counting principle that will make our work a little bit easier. So the first example we're going to do it's your birthday. You get to choose a cake. You can have a round or rectangular cake. The flavor can be vanilla, chocolate, or lemon, and the icing can be butter, cream, chocolate, or cream cheese. How many different cakes are possible? If we use the information we learned yesterday about making a tree diagram, we did vertical tree diagrams yesterday. You could also do them in a more horizontal. So we could start with the shape, and that could be our first level, round or rectangular. From there, we have a choice of flavors, and there are 3 flavors we can choose from. So we could have vanilla, we could have chocolate, or we could have lemon. Each shape has a choice of 3 flavors. Once I've picked the shape and the flavor, I get to pick my icing. My icing can be buttercream, it could be chocolate, or it could be cream cheese. So each one of these can have another 3 branches coming off. Chocolate or cream cheese, buttercream, chocolate or cream cheese. And then if we count the very last branch, we could get our total. So we have 3, 6, 9, and then 3, 6, 9. So we have a total of 18 cakes or possible ways to choose our cake. Okay, so let's take a look. I have a video for you to watch. There were 18 cakes.
Area code and can issue new 7-digit phone numbers. All phone numbers are equally likely. So we have 3 parts to this problem. First, A, we need to find the number of possible 7-digit numbers. B, we need to find the probability of being assigned the phone number 333-6789. And lastly, C, we have to find the probability of a phone number that does not contain a 5. All right, so first, let's take a look at the fundamental counting principle. So, if there are m ways to choose a first item, okay, so m ways to choose your first item, okay, and n ways, okay, to choose your second item, okay, after the first item has been chosen, then that means, okay, there are m times n ways to choose all items, okay? And this is known as your fundamental counting principle, okay? All right, so let's take a look at A. All right, so find the number of possible 7-digit numbers. So we're going to use the fundamental counting principle and multiply the number of choices in each category. So here we have, all right, our category. So we have our first digit, and there are 10 possibilities, right? Our second digit, 10 choices. Third digit, 10, and so forth, okay? We go from 1 digit all the way to 7 digits because we have 7 possibilities for 7-digit phone number. All right? So now what we're going to do is we're going to multiply the number of choices in each category. So we're going to take 10 times 10 times 10 times 10 times 10 times 10 times 10, okay? And that is going to give us 10 million, okay? So the number of possible 7-digit phone numbers is 10 million, okay? All right, so let's move on and let's find the probability of being assigned the phone number 333-6789. All right, so since the number 333-6789, I'm just going to give myself a little more room here, okay? Since the phone number 333-6789 is unique, there's only one possible way it can be chosen, okay? So that means the phone number, okay, our possibility, 333-6789, all right, equals our one possibility, okay, because this is so unique, over the number of possibilities, okay, or the number of possible phone numbers, okay? So we know that the number of possible phone numbers is 10 million, right? So we're going to have 1 over 10 million, okay? And then that would give us 0.0000001, all right? So this is the possibility of being assigned this phone number, okay? So here is our answer right here. All right, let's move on to C. So here we need to find the probability of a phone number that does not contain a 5. So first, we're going to use the fundamental counting principle to find the number of phone numbers that do not contain 5. So for each digit, there are 9 choices except 5, right? Because you have 1 through 10, right? You have 10 choices, okay? But for each digit, there are 9 choices if we take the 5 out, right? So now what we're going to do is we're going to take our 7 digits, because we have a 7-digit number, right? And instead of multiplying it by 10, we're going to multiply it by 9. So we're going to take 9 times 9, 9 times 9 times 9 times 9, times 9 times 9, that's 1, 2, 3, 4, 5, 6, 7, okay? And here we get 4,782,969, okay? So now, all right, we're ready to find the possibility of getting no 5s. So the possibility of getting no 5s, here we're going to take our number, okay? This is the number of times that it could happen over our total number of possibilities, right? Okay. And we get, this is roughly about 0.478, okay? So the probability that a phone number does not contain a 5 is 0.478, okay? All right, so things to keep in mind, remember, all right, that if there are m ways to choose a first item and n ways to choose a second item after the first item has been chosen, then there are m times n ways to choose all the items, and this is known as your fundamental counting principle.
Okay, let's try an example. You are now going to need to choose a computer password that has 2 uppercase letters followed by 4 digits. How many possible passwords are there? So there's not a probability question in this example. Chances are today we're just going to get through. Okay, after watching that video, let's see if we can try example 2. And I'll go ahead and explain it the way I would explain it for you. You need to choose a computer password that has 2 uppercase letters followed by 4 digits. So what we need to do for this counting principle, she explained that it is multiplying the number of choices you have for each event. So I like to describe what the events are. I am picking 2 letters and 4 digits. So I kind of sometimes even draw these lines to represent that, so I know how many factors I will multiply because of how many choices I will be making. Those 2 lines represent my letters, and then I have 4 digits. Okay, so I am multiplying 1, 2, 3, 4, 5, 6 things together. You can also see that by adding 2 and 2. It's like 6 choices you have to make. So the choices for the letters are that there are 26 letters in the alphabet. So I would have 26 letters to choose from for my first choice. And then, second letter, it didn't have any exclusions or say anything about not being able to be repeated. I would have 26 letters for my second choice. And when we get to the digits, we know that there are 10 digits because they have to be a single digit and it counts 0. So if you count them up, 0 through 9, there are 10 choices to be made. And again, no exclusions. So you can see pretty quickly how fast these multiply, this multiplication property. And when you multiply all those together, you should get there are 6,760,000 possible passwords out there. Okay, so let's take another look at another example. You're going to randomly choose a 7-digit code to open your garage door, and what is the probability you choose the code 1, 2, 3, 4, 5, 6, 7? This is just like her video. The 7-digit garage code and the 7-digit phone number would have the same number of total possible outcomes. Because there are 7 digits that I am choosing, I have 7 things that I am multiplying. And I'm choosing digits. It doesn't say anything about repeating them. So I have 10 choices each time, or the total possible would be 10 million. Okay? Since there are 10 million, the probability of picking this one unique one, so the probability of picking a 1, 2, 3, 4, 5, 6, 7, or, yeah, we don't need those, I guess, because this is just a code, would be equal to 1 out of the 10 million. And we will leave ours in fraction form. No need to change it to a very long decimal. Example 4. In this case, we are rolling 3 number cubes. What is the probability that all 3 are the same? So we first have to look at what are the total possible outcomes here when I'm rolling 3. There are 6 sides to each cube. So there are 3 cubes being rolled, so it's kind of like having 3 events. Since there are 6 possibilities for the first cube, 6 for the second, and 6 for the third, we multiply those and get a total number of outcomes of 216. Now, maybe you want to make a list of what your favorable outcomes are. So I could roll a, let's try this differently. I could roll a 1, 1, 1. I could roll 2, 2, 2, 3, 3, 3, 4, 4, 4. These are all the favorable outcomes, or finally the dreaded 6, 6, 6. So if I count up the favorable outcomes, I have 1, 2, 3, 4, 5, 6 total possibles that could be the same number on each cube out of a total of the 216. Again, I'm dividing top and bottom by 6, and I would get 1 out of 36 for my total probability that all 3 cubes are the same. Okay, what if we flip a coin 6 times and I want to know the probability of getting tails each time? So that would be, there are 6 events that are taking place, 6 flips of the coin. Okay, so I have 1, 2, 3, 4, 5, 6. My total number of outcomes are that every time I flip it, I have a choice, heads or tails, heads or tails, heads or tails, would be, so I take this 2 total outcomes each time I flip, and I get a total possible outcome of 64. Okay, and the probability of getting my tails each time, right, is that I'm going to have 1 out of 64 because there's one way to get tails, and it doesn't matter. I can multiply 1 times 1 times 1 times 1. I'm always going to have 1 out of 64 for this one. Okay. Another way to do that, if you look at, you can always multiply your probabilities together. The probability that I get tails the first time is 1 out of 2. The probability the second time, and again, you keep going because this is just multiplying the probabilities is the same type of thing. Okay. And that still gives me the same answer, 1 out of 64. Okay, we're going to watch another video.
Now let's learn about compound events using the fundamental counting principle. We're talking about probability here. And the problem says that the following experiment is going to be performed. Step 1, we toss a fair coin. Step 2, we spin a spinner, which has got 4 possibilities, red, yellow, blue, and green. And the third part is choose a marble, which is gray, pink, or black. The question says, what is the probability that the coin will show heads, the spinner will land on blue, and a black marble is chosen, right? So we are looking for heads, blue, and a black marble, right? That's the combination we're looking for. It's the compound events. So what is the probability of these 3 events occurring in succession, right? So let's learn how to do this. One way of doing this is let's make an organized list or a tree diagram. So what I'm going to do is let's say the tree diagram has heads and tails as the possible outcomes of the fair coin toss. Then in the spinner, with heads, I can have 4 possibilities, which are red, yellow, blue, and green. Then with tails, I've got 4 possibilities, which are red, yellow, blue, and green, right? Then for each one of these, we can have 1 of 3 possibilities, right? We can have a gray, we can have a pink, or we can have a black marble. Similarly, I'll have 3 here, 3 here, 3 here. R, P, B, L, R, P, B, L, R, P, B, L. You get the idea. Similarly, here, we can have 3 for each. Red, gray, pink, and black. Here, I can have 3 more. Gray, pink, and black. You get the idea, right? This is gray. Right? So ultimately, when I look at it, there'll be 3, 6, 9, 12, 15, 18, 21, and 24 possible outcomes. 24 possible outcomes. Okay? We are looking for the outcome that lands on blue, black, and the coin showed heads. So heads, let's change the color of our pen. Coin should show heads, the spinner should land on blue, and the black marble should be chosen. That's 1 possibility out of 24, right? So the probability of heads, black, blue, and black is 1 possibility out of 24, right? There's only 1 possible combination that'll give us that out of the possible 24 combinations. There's another way to do this though. We can look at the number of ways this can have an outcome. There are 2 possible outcomes here. When I spin the spinner, there are 4 possible outcomes. And when I choose a marble, there are 3 possible outcomes. If I multiply 2 times 4 times 3, we get 24 possible outcomes. Instead of writing all of these, we can simply use the fundamental counting principle, which says in case of these independent events, we can multiply the total number of outcomes of each event to get the total number of possible outcomes for the compound event. So that's 24. Now, out of the 24 outcomes, what is the possibility of how many events are favorable to us? Heads, blue, and black, which is 1 of the 24, right? So the probability is 1 over 24. Probability of the compound event that we were looking for.
So for our final example of the day, let's look at flipping a coin, rolling a six-sided cube, and spinning a spinner that is divided into 8 equal parts and labeled A, B, C, D, E, F, G, H. We want to find the probability of flipping heads, so our probability is going to be flipping heads, rolling an even number, and spinning a vowel. Okay? So instead of making the tree diagram, we can first, let's look at all the total possible outcomes. So when we have 3 events that we're going to multiply. So basic counting principle in this case is going to be when we flip a coin, there are 2 outcomes. Roll the cube, there are 6. And because the spinner has 8 equal parts, there are 8. So when you take and do your total possible outcomes here, you're going to take your 2 times your 6 times your 8. We know that there are 96 outcomes that are likely. Now, flipping a coin, we start to determine then the favorable outcomes that we get a heads would be one way. That we would get an even number, well, there are 3 ways to get an even number. So for the favorable events, we have one way to get a heads times the even number is 3, and then times getting a vowel, well, A and E are only 2. So there are 6 favorable outcomes. These are the favorable outcomes. So the probability could be written like this: 6 out of 96. Again, divide by 6, and you will get 1 out of 16. Okay, and then I also showed you about when you're doing compound probabilities, you can look at each scenario here and look at the probability of getting a heads. Well, that's 1 out of 2 times the probability of getting an even number is half again, or 3 out of 6. And then getting a vowel is the 2 out of 8. Again, if you reduce these down, you won't have to simplify in the end, but we can get the same thing, which simplifies again to 1 out of 16.